Good afternoon.
Hello, Kim.
Hi.
So, Kim Vanmeensel is our next speaker, and he's professor at the University of Leuven in Belgium. So not the same as me. He's the Flemish part, I'm in the French-speaking part. But it used to be the same universities in some time ago. And so he's involved in the Metallurgy and Materials Engineering Division, and he will kindly talk to us about LPBF of copper-based alloys, which is quite a challenge for thermal transfer applications. So Kim, if you can share your screen there.
Okay.
And
thank you, Aude. Thank you for the introduction as well. So we're quasi neighbors. You all see my screen now? I think so.
Yeah, it's all working, please.
Yeah, so I was going to talk about laser powder bed fusion processing behavior of highly reflective alloys, and we chose copper-based alloys. And actually, this is a kind of a summary of one of our PhD students who will soon defend his PhD. So with a clear application in mind, which was heat transfer applications, and if you want to make it even more concrete, liquid-liquid heat transfer device, which has to simultaneously operate at an as high pressure as possible and has to maximize the heat exchange capacity. So I will come back to that later. So Suraj is the person who performed most of this work. And yeah, I'm actually very grateful for the things he did. So, also, here's my pointer. So what I will talk about is very briefly introduce a bit why we choose copper-based alloys for these kind of applications. Since especially when we want to process copper-based alloys or highly copper-based alloys with high reflectivity using a near-infrared fiber laser, I think we should say a few words about how a laser beam interacts with a powder bed and also with a melt pool. I will talk a bit about powder surface modification techniques, their limitations and their benefits. Very shortly, something on how we can characterize very fine precipitates in an SEM using still Kikuchi diffraction patterns. And I will summarize a bit and compare different alloys which we produced and then their behavior upon heat treatment. So focusing on basically finding the best compromise between a good quasi-static mechanical behavior and a good thermal conductivity. And as you know, for metals, electrical and thermal conductivity go hand in hand. So this is actually an introductory slide which I use in one of my bachelor courses, where we try to explain students why they should look at material properties for a certain design. And this is for a tube-in-tube heat exchangers with two liquids flowing, so a cold and a hot liquid. And as you see here, the amount of heat which you can exchange is linearly dependent on the thermal conductivity of the material which separates the cold and the hot stream. And it's also linearly dependent to the yield strength of the material. So that basically means the thinner you can make the separation wall, the more heat you can exchange. But of course, the separation wall has to be strong enough to withstand the pressure acting on it. And there are hoop stresses acting on it. And they should not exceed a yield stress, because otherwise your plate will plastically deform, which you don't want in this case. So if you want to maximize this Q, so the amount of exchanged heat, you see, you can work on the material. And of course, you can also work on the design. And that makes the combination of highly conductive and strong alloys with design freedom, geometrical design freedom, and then we immediately talk about additive manufacturing technologies, very interesting. So this talk will mainly focus on the material aspects, and I will just show a few slides on the geometry design aspects. So a small recap for most of us, this is from the same course. So basically showing the different effects of strengthening mechanisms, starting from pure copper with a fairly low yield strength, but a very high electrical conductivity, and how the different strengthening mechanisms influence both these material properties. So you notice if you form solid solutions, you can strengthen the material, but you significantly compromise on its conductivity. On the other hand, introducing more dislocation and dislocation structures will work hard in the material. It will get stronger with minor influence on the conductivity, and then a kind of compromise between both of them in terms of strengthening effect. Probably the strongest are precipitation strengthened systems with an average effect on the conductivity. So that was the intro for the material aspects, and then 2 slides on the design aspects. So we look into the design of lattice structures where these 2 fluids can interact very intensely. And one kind of lattice structure you could use for that, because it aims at optimizing the surface area per unit of volume. And that is the so-called triply periodic minimum surface functions, which are basically a combination of trigonometric functions in 3D. And the most simple one is the primitive Schwarz surface, for example, which is just a combination of 3 cosine functions in 3 directions, equaling a certain constant, and you can play with this constant, and as you modify the constant, you actually change the fraction of the 2 composing volume units. And so that is shown here. So what this graph plots is a ratio of surface area over the volume of such a unit cell. And so you see that when your constant C in your phi equation equals 0, you maximize the amount of surface area. And the different abbreviations here, they stand for different unit cells, all with different geometric functions. And so the S type, I'm not going to go in details here, maximizes the surface area. Now, so here you see basically when you construct these kind of surfaces, you create 2 types of domains, and by varying the C parameter in your function, you vary the volume fraction of each phase. So this allows you also to structurally design, for example, in certain regions of your heat exchanger, there are certain mechanical requirements, and then you can, for example, increase the fraction of solid phase to provide more strength. So you can also make graded structures as such. This can all be expressed as a mathematical function or a combination thereof, and you can describe it in an STL file, so you can directly load it in your printer. And so a case study is like, could we at the same time optimize surface area over a mass, because this was for a lightweight application, and this appeared on this website as well. Now, going to the materials aspect, which is the focus of this point. So first of all, when we talk about copper and copper-based alloys, of course, you need an adequate powder, which we, in most cases here, atomize ourselves using a conventionally closed-coupled gas atomizer. And the challenges related specifically to copper, you all know in solid state, copper is a good conductor. So when you build it on a base plate, and we preferentially wanted to use copper-based base plates not to contaminate the bottom layers of the part, you know that there is a lot of heat dissipation in vertical direction. So it might be optional to have to preheat your base plate to avoid the very rapid heat dissipation. And that is foreseen in one of the non-commercial machines which we use and which were initially developed by our colleagues from the mechanical engineering department. Now, the major challenge when we're using normally near-infrared lasers with a wavelength emitting laser light of about 1060 to 1070 nanometer, and you see it here. So this is the fiber laser wavelength which we use. And copper, for example, this curve has a very low absorption. These are curves for flat plates, very plumb parallel, nicely polished. So they have a very low absorption. And how can you mitigate that? You could alloy the copper, of course, especially with elements in solid solution, but you just know, or I just mentioned that when you do that, you will compromise on the conductivity. We could also modify the laser source. So there are, for example, these days, more and more powerful green and blue lasers. And you see that at these wavelengths, for example, so a green laser is, for example, located somewhere over here. There, copper already absorbs much more of the laser lights, and it will be even stronger with the blue laser. And by the way, you notice the similar problems for gold and silver. And as I will explain later, it's all related to the electron configuration of the material. So if we look at how such a material interacts with the laser beam, there are intrinsic and extrinsic parameters contributing to absorption phenomena of a material in general. And the intrinsic ones, they are labeled here. So there are intraband electronic transitions and interband transitions. So that is purely related intrinsically to the band structure of a metallic lattice. There is also the anomalous skin effect. And then the external properties are, for example, the surface roughness of a plate or also of a powder, for example. Its oxidation state, if a copper oxide layer with another absorption behavior is present, of course, it will increase the absorptivity. And all kinds of impurities and defects at the surface will, of course, also influence the absorption behavior. So intrinsically, and this is shown here, in the infrared region, there are not a lot of electrons contributing to the absorption of laser light with an infrared laser, wavelength. So both copper and silver by nature will not absorb a lot in the infrared or near infrared region. What can we modify? Of course, we can modify the surface roughness. We can introduce oxides on the outer surface of a plate, or as I will show later, on a powder bed, and all kinds of impurities, which could also be alloying elements. Now for flat plate absorption, you have the Fresnel equations, which are only valid for wavelengths above 0.5 micrometer. And when you plot them for different materials, you again see similar curves as I've shown before. And you see, for example, copper here has a fairly low absorption at the infrared laser wavelengths. So you see that other elements absorb much better, and that's usually why titanium alloys or iron or nickel-based alloys, they don't exhibit too many problems when processing them in terms of absorption, I mean, and in terms of power you have to supply when processing with a near-infrared laser, but copper, silver, and gold are problematic. One advantage we have is your laser beam does not shine on a flat surface, it shines on a powder bed and on a melt pool. So for a powder bed, it has been shown theoretically, and I should mention a reference here, that the laser absorption is enhanced due to intrinsic scattering in the powder bed itself, up to a factor of 6 or less for copper. So that meant for a near-infrared laser 30% absorption in a powder bed. But if I remember well, Professor Logé yesterday also talked about absorption phenomena, and he also pinpointed the fact that your laser beam is actually, for the majority of the beam, is shining on a liquid melt and not as such on a powder. And so the advantage of a powder bed is then completely annihilated, and we should try to improve, especially the absorption behavior of the melt pool. When looking at powder, it's fairly easy to increase its optical absorption. So you see here a comparison between absorption curves between pure copper and oxidized copper powder. And you see that in the powder state, of course, at the near infrared laser wavelength, there is a clear increase in absorption behavior. If the laser would shine only in powder, this would probably provide a solution. But the question still is, what will happen once everything is converted into a melt and your laser shines on the melt pool? To give you, so you can, one way to do it is, of course, to introduce roughness and impurities at the powder surface. We first tried to process pure copper with a very powerful laser, so 1 kilowatt laser, near infrared laser. This was atomized copper powder from OF copper, and you see that during atomization you pick up some oxygen, so the powder had about 50 ppm of oxygen in the powder state, and then you see the processing conditions here at high laser powers and very low scan speeds. We managed to fully densify pure copper, which was in a way good news. There was also some bad news. So the good news was, okay, we achieved high relative densities. Something I should mention here, we used a relatively broad laser beam of 60 micrometer, but we observed some optical damage in the optical system of the laser powder bed fusion machine due to back reflection. What we did then is we modified the beam diameter to focus the energy input more. We also modified the optics so that the back reflection was not directly shining on the mirror, and that is thanks to the help of the people of the mechanical engineering department. And then you notice that you could successfully process copper at a lower power level of 500 watts and a scan speed of about maximum 800 millimeter per second. But when you look in detail at your melt pools in your microstructure, they are very deep. So you typically, from the welding literature, you define a kind of ratio, which is the depth over half width. So that's the R value, and that is very high and certainly higher than 1, which is typically in the so-called keyhole mode and not anymore in the conduction mode. And when you make a plot of laser power versus scan speed and you compare all the microstructures you generate, then you see that we could only successfully process pure copper in a very narrow processing window, which was really at the transition between conduction and keyholing mode in the keyholing regime. But as mentioned here, prior to the onset of keyhole-induced porosity. But so that meant that your processing window was really small, and that was very challenging. So we are looking for ways to more sustainably process. But one thing we learned also is, look, your melt pool shape also has an influence on your absorption behavior, and there is literature available on that. So as the aspect ratio of your melt pool increases, so as the depth increases and you evolve towards more keyholing mode, you see a net increase in your absorption behavior. So besides pure intrinsic and extrinsic effects, as your laser beam also shines on the melt pool, the shape of the melt pool also has a very strong influence on your absorption behavior, which is something to bear in mind. Takeaway messages so far: it's feasible to process pure copper, but it's challenging. You might damage your machine, so you have to be careful. And at the moment, we're still talking about pure copper, which has a good conductivity for sure, but in terms of strength, it is not that promising. Now, further elaborating on the idea on surface modification of powder particles, we were first thinking about how deep does such a laser beam actually interact with the material, and it's not deep at all. So you see that the optical penetration depth calculated using Lambert-Beige law for different materials is in the tens of nanometer range for many materials. So that would basically mean if you modify the outer few 100 nanometers of a powder or of a solid substrate, you would already see a significant effect. Another thing to bear in mind, thinking about the idea of surface modification of powders, anything you introduce into your powder will have an effect on the conductivity. And especially the solid solution forming elements such as nickel, they have, so this is for elements all in solid solution. Nickel has a significant effect, and you see other elements such as phosphorus, which is often there as an impurity, or titanium or chromium in solid solution. They have very limited solubility, but they do have, and they have a very significant effect on the conductivity. Of course, at even higher nickel content, since nickel and copper are mutually soluble over the whole solubility range, there is a very drastic increase in conductivity from the moment you exceed a few percentages of nickel. The first attempt we did was coating copper powders using a precipitation method, so that we would precipitate nickel hydroxide and then do a hydrogen reduction. And you see the EDX nickel maps, they clearly show that every particle is nicely surrounded by a nickel layer. So in that sense, our particles were nicely coated, and you also visually saw that. So this is the original copper powder on the left-hand side here. And then once you coat, the color really changes. And this is, by the way, as a reference, an pre-alloyed gas-atomized copper 10 nickel powder. So you see that a powder with an overall content of 0.26% nickel already looks much darker as compared to one with 40 times as much nickel content, but homogeneously mixed in the powder. And you also see that in the absorption behavior. So you see that a coating layer in this case, it would be a few tens of nanometers, drastically increases the absorption from this level to this level. So for the powder absorption, this was certainly beneficial. We started processing parts with this, and we noticed that it was feasible to process parts at significantly lower power levels as compared to the pure copper. This was still with a 60 micrometer beam diameter and at average speeds. Of course, your nickel content is very low, so your mechanical properties are not so fantastic, and especially we were worried about the ductility, and we noticed that this was basically, since there is a hydrogen reduction step involved, this is due to hydrogen embrittlement. So if we would ever think again about nickel coatings, we would not take the precipitation plus hydrogen reduction route. Besides that, the interstitial hydrogen also has an influence on the conductivity, because this decrease with respect to pure copper is too much for the nickel content present in this. The most simple way to improve the optical absorption of a powder, of a copper powder in this case, is simply to oxidize it. And so you noticed in XRD that there were copper oxides present at the powder surface particle. You also saw that in the powder state, the optical absorption was increased. And again, we could process this alloy at fairly mild laser powder bed fusion conditions, I would say. So again, about 500 watts of power with a scan speed of 700 millimeter per second. This is a summary of the properties we obtain. And of course, again, the oxygen content is not very high. You have some copper oxides. We could find them back in the solidified parts. So they are there as a kind of Roland strengthening particles. But of course, their strengthening effect is not huge. And yeah, so we are still talking about yield strengths which are about double of pure copper, and an elongation at break which was about half the one of pure copper which you expect. For example, this is an EBM pure copper result. Now, you might think, look, whatever you do to your powder which increases the optical absorption will be beneficial, and I intentionally show this slide to make a statement that that is not true. You could simply coat your copper powder with pure carbon, and as such, as you see on the left-hand side, you clearly increase the optical absorption of the powder beds at the near-infrared laser wavelength. But in terms of processing behavior, we needed, again, the same level of very high power levels as we needed for the pure copper at very low scan speed, so resulting in very high volumetric energy density. Besides that, since there was still carbon present, liquid copper and carbon do not wet each other, we could find back carbon at the borders of every melt pool. So it basically means from the moment your laser beam irradiates your carbon-coated copper powder beds, you create liquid copper at a certain point. No wetting occurs between the solid carbon and the liquid copper. The carbon segregates the melt pool boundaries, and your laser effectively shines on a very pure copper melt with all its consequences, meaning a lot of back reflection and the requirement for very high laser powers. So whenever or whatever you do to your powder particle, you have to make sure that there is still an effect of that in the melt pool itself. And so it seemed to work for nickel, it seemed to work for what we showed before for oxygen. And that is basically because copper and nickel, they form a solid solution also in the liquid. For the oxygen, copper oxides are fairly well wetted by liquid copper. So we think that they could still play their role from the moment they were sucked, because there is a suction effect, as I will show later. From the moment that these modified, surface modified powder particles were sucked into the liquid melt pool, they could still play their role as absorption enhancing medium, which was not the case with carbon particles, which immediately segregated and which did not contribute to any enhanced absorption. So that's the takeaway message number 2. It seems to work for some surface modifications, but for example, for pure carbon, it did not work. And so there are other effects playing besides the pure optical absorption in the powder bed. And one of them is the effectiveness at which a surface decorated or surface modified powder particle is incorporated in the liquid melt. So there are wetting phenomena playing there as well. Besides that, since we are dealing here with alloys, then with a maximum alloying content of nickel of 0.3%, of oxygen, same order of magnitude, and for the carbon, also something similar, their strengthening effect is very small. So when you look at your heat exchanger performance, which is a combination of conductivity and strength, it's still fairly low. And remembering the slides where you wanted to find a compromise between strength and conductivity, precipitation hardenable alloys are, of course, much more interesting. So instead of starting from pure copper, we started to play with a low alloyed copper 1 chromium powder. And also there we applied surface modifications, because that powder itself still has a fairly low absorption, because 1% of chromium does not contribute. But when you carburize, and how did we carburize for it? So we did not simply coat it with carbon. So the first step was coating, but then secondly, we applied a heat treatment. So that chromium actually diffused from the inner side of the particle along the grain boundaries to the surface of the powder, and there chemically bonded with carbon to form carbides. So we also found carbides at the outer surface of the particle. So this is a FIP cross-section of such a particle. This is the coating layer, but so here you see that there is a reaction layer. And if you would look in more detail along the grain boundaries of this copper particle, you would find a lot of chromium segregation. So first, there is a chromium carbide layer, a small chromium depleted zone, and then a lot of copper enrichment because of chromium enrichment because of chromium diffusion along the grain boundaries. So during this carburization heat treatment, you basically diffuse out chromium, which binds to the carbon which you decorated the powder with, and you form carbides. And these carbides, they are again well wetted by liquid copper, so they were very effectively incorporated in the melt. So if you compare the processing conditions for the pure carbon mixed copper chromium 1 powder and that powder with additional heat treatment to form carbides, you see the processing behavior here. So we compared similar power levels with a power level of up to 400 watts and very slow scan speeds, resulting in very high volumetric energy densities, we could maximum achieve parts with 96% density. While if you do the same, even at much lower volumetric energy densities, which means at much higher scan speeds, we have a fairly broad processing window where we can sustainably process these carburized copper chromium 1 powders. Now, a few words. So these powders, we were wondering, is the chromium now present as metallic chromium in your processed part, or is it still there as carbides? And for the carburization heat treatment, so we developed a technique where we partially etched away the surrounding copper matrix so that we could do TKD on single precipitate particles. And as you can see, they are sub 100 nanometer. And using this selective etching technique and then collecting Kikuchi diffraction patterns from the particles, we could identify their crystallography. And we found 2 types of carbides, so either chromium 1 carbon 1 or chromium 3 carbon 2 carbides. So you could still find these carbides in the laser powder bed fusion processed parts, which means that at least part of the carbon remained there as carbides. They reacted to heat treatments, and so what we often compared is a conventional solutionizing plus H-hardening heat treatment with a direct H-hardening treatment because of the very high cooling rates during laser powder bed fusion. You supersaturate your matrix, and there is a fair chance that this is probably more efficient than a separate solutionizing heat treatment. And you have actually more control of the size of the precipitates you form there. So in this case, we formed a material with a very interesting combination of yield strength and tensile strength, also quite decent work hardening behavior. This is in the direct aged state combined with an electrical conductivity of about 75%, which corresponds to a thermal conductivity of about 350 watts per meter Kelvin. In the solutionized plus H-hardened state, your precipitates grow more, you have a more purified copper matrix, so your conductivity increases a lot, but you compromise on the tensile strengths. So as for heat exchange applications, you basically look at the combination of conductivity, then thermal and strength. We would probably opt for this material. Now, this is where we made a hypothesis on why the carburized particles worked and the carbon decorated particles did not work. And if you look in literature, people discuss the flow behavior due to evaporated metal very near your melt pool. And actually there you can differentiate 3 zones. So this is furthest away from the center of the laser beam, and this is exactly at the center of the laser beam. So you have zones where there is an attractive force and where there is a repulsive force, and in zone 3 there is an attractive force again. So we believe that for the carbon decorated powders, due to these forces acting on these powder particles, we lose the decorated carbon and we basically suck in pure copper chromium powder again, which does not contribute at all to an enhanced absorption. While if we carburize the powder, the carburized layer stays there because we could still find back carbides after laser powder bed fusion. And we think that basically you suck decorated powder particles in your melt pool, which effectively contribute to the enhanced absorption. A similar thing we did with nitridation. So instead of first coating with carbon and then doing a heat treatment, we directly heat treated the copper chromium 1 powder in nitrogen. And you see that as your heat treatment temperature increases, the optical absorption of your powder also increases. And same phenomenon was observed. At the outer surface, you find chromium nitrides in this case, and you find a lot of chromium diffusion along your grain boundaries and very near your surface chromium depleted zone. So very similar working principle. Here you see a detail. So all the black dots here along these grain boundaries are chromium. You have a surface reaction layer, which is mainly chromium nitride, and this is the chromium depleted zone. Again, this enhances absorption a lot, and the thickness of the layer could be controlled because it really matches very well with, you can control the chromium diffusion behavior simply by calculating it with fixed second law of diffusion. So we have a control over the thickness of the layer. So that also means we can vary the ratio of chromium, metallic chromium to chromium nitrides. And we know also how deep a laser beam can penetrate in chromium nitride and chromium. So we have a fairly good idea of how we should surface treat these powders in nitrogen. Now coming to the properties again, you see that you have a clear nitrogen pickup in your surface modified powder, but you lose most of the nitrogen again during laser powder bed fusion. So that also meant that in our LPBF parts, contrary to the carburized powders, we didn't find a lot of nitrides anymore. The majority of chromium was present there as metallic chromium, which made it, of course, available for heat treatments, precipitation hardening heat treatments. And yeah, so these are the combination of properties we achieve for this type of alloy. Now, in summary, these are all the alloys that Suraj worked on during his PhD. And so we were always trying to look for what is here on the upper right corner. So meaning a good combination of thermal conductivity and yield strength. And so what we agree upon is that probably you need a heat treatment, and most probably direct edge hardening is the desired one because it really maximizes your strength. So the highest strengths were always achieved with the direct edge hardening heat treatments. That does not necessarily mean that it always had the highest conductivities, as you can see here, but the combination of both was usually better there. So in overall summary, I think Suraj managed to process a very reflective and conductive powder at very high scan speeds in a very reliable way with a near infrared laser with a maximum output power of 500 watt and a very fine beam diameter of maximum 50 micrometer. And that is for an industrial application and for somebody who wants to use this, very interesting, I think. With respect to powder surface modification, as I've shown, it can work, but there is more. It's not only the powder, it's also how the surface modified powder behaves whenever it enters the melt pool. And yeah, you typically, if you want to maximize your strength, you go for a direct edge hardening heat treatment. If you want to maximize conductivity, you solutionize first and you edge harden. If you look for a combination, probably you will go for a DA heat treatment. These are a few parts which Suraj also made. So radio frequency antennas, and what is very important there is that they are very straight. And surprisingly, in copper, actually, in general, in the highly conductive copper, the residual stresses in your parts are surprisingly low, despite the fact that it's a very high conductor and the large heat dissipation. We also patented part of the procedures here, so you know, that is nice as an output. So I think I should acknowledge him for his work. His name also means the sun, and he's finalizing his PhD now. So I took a picture because there is sun at the horizon right now. If you want to read some of his papers, you can find them in Google Scholar, and I should also thank, for sure, people who contributed to the research. So there are 2 postdocs, 3 postdocs, and a PhD student. The people from the mechanical engineering department for providing machines, and some funding, of course. And thank you, organizers, especially Aude, for inviting me. I think I followed a few talks and they were very interesting. So feel free to ask questions as well.
Thank you very much, Kim. You did interesting work and very impressive results. I had seen some of it some time ago. It's even improved now. It's a very reactive, very reflective material that is very difficult to process. Do we have some questions from the audience? Eric?
Yes, just a general question, because I worked some years ago about GlidCop, which is a ODS copper-based alloy. And I was thinking about the talk of Christian this morning, and I was wondering if you think it could be possible to produce such ODS copper with the same process, but just by introducing, if I remember, it was alumina in this GlidCop. And because it has very nice properties, mechanical and thermal properties.
Mm-hmm. I can imagine, yes. Of course, you need some kind of control over the alumina grain size, then I guess, in order to enhance its strengthening effect. But
yeah.
Sure, you could start with a pre-alloyed copper aluminium powder, and you could perform a heat treatment in oxygen, and I think you can have a certain kind of control over the alumina grain size then.
Okay. No, I think it could be very nice because it's well used ODS copper alloy in, I think, in nuclear engineering and some other application.
Of course, yeah. I can imagine that there also the location of the oxide is important, and I would think you preferentially want it along the grain boundaries. And then, yeah, thinking about the way it would solidify as well. I have no idea about exactly the wetting between copper, aluminium, and alumina. And whether it could act as a heterogeneous nucleation site or not, but that will determine whether it will appear along the grain boundaries or more inside the grains, I think.
Okay, thanks a lot, Kim.
I guess this might also change the interaction with the laser in some way. Maybe not so much because it's just a low volume fraction.
Yeah, but indeed, I mean, for us, it was also surprising to see, especially in the powder state, and that even an overall, for example, nickel content of 0.3% can drastically enhance the absorption behavior in a powder bed, of course. And then the question was, can it still be efficient enough in the melt? And it seems to be. So it would be very interesting to collaborate with people who, for example, in a synchrotron, who could in situ visualize what is happening in these melt pools. And I
had some presentation yesterday that we're able to do that.
Yes.
Collaboration is needed here.
Yeah, indeed.
Yeah, we've seen in zirconium containing aluminium alloys that we use for inclusions and for grain refiner that indeed it changes the interaction with the laser, and the processing conditions are different actually. So I think I see the same for aluminium. I see that Roland has raised his hand.
Yes, Roland? Thank you. Thanks a lot, Kim. Very interesting. We have been working also on highly reflective materials, more like gold alloys. I was just wondering, at the beginning, you showed that when you really deal with the pure copper, that you actually need to go in the keyhole mode to be able to really process it well. But it's very close to the transition with the conduction mode. And then you mentioned what goes on the liquid and on the powder, which I also discussed a bit yesterday. I was wondering if you try to change very much the combination of power and velocity, because that can have an influence on the part of the laser beam that goes on the liquid and on the powder. And the more you go on the powder, the better it is. And this might help moving maybe a little bit towards the conduction modes.
Yeah, so you are saying move towards higher power levels?
Actually, yeah, it's a combination. If you play with the power and the velocity,
Yes.
on the principle, there is a direction in which you increase, you can see that in the simulations, where you increase the part of the laser beam that goes on the powder.
Okay. Yeah, then I agree with you that a modified powder should be even more beneficial.
It should be beneficial in all cases, but I guess it's
yes.
Yeah.
But yeah, for the.
I mean, you solve the problem differently, but if we remain on the pure copper, there is not so many solutions except playing really on that.
Yeah, yeah. There are the solutions which I also saw besides that in literature is. Try to have thinner layers of powder and slightly finer powder size distribution, so that you, first of all, do not have to penetrate that deep into a powder bed. And secondly, that you increase the internal scattering because of finer powders. Of course, you still have to be able to spread them. Another solution which I saw is also people building on stainless steel base plates, because the heat dissipation in your part is less than. So you accumulate a bit more heat in your part, and the average temperature of your part during the whole process remains higher. And then, yeah, of course, changing laser type. That these are solutions which I've also seen. Yes. But green lasers at the moment, they are not that powerful yet, and they are the beam quality is not that good, and they are still expensive.
But there is a commercial system with green laser that came out, I think.
Yeah, from Trumpf. Trumpf has one, I think.
I think so, yes.
On the other hand, like, I think the solutions which we provide, they also work for silver and gold. And with a green laser, for example, I don't think you would be able to process silver, because yeah, that even at the green laser wavelength, silver does not absorb a lot. For copper, there is a substantial increase already, but for silver, not.
Okay, thank you very much.
Thank you. So gold in Switzerland and copper in Belgium. I'm not surprised. Huh?
We wanted to do a lot of tests with gold and silver. The poor Belgians stick to copper.
It's a bit expensive if you don't have a sponsor. Huh?
Yes.
Eric is willing to ask a question.
Thanks a lot for the very interesting talk. I mean, if I wanted to replicate this to some extent, I suppose you can't go ahead and buy nitride or carburized copper powder, right? So from a very practical point of view, what is required to make these kind of modifications?
A furnace where you can shake or rotate your low alloyed copper powder, which should contain an alloying element which can bind nitrogen or carbon, and you supply the nitrogen as nitrogen gas.
Mm-hmm.
We did it by carburizing it, but I think if you have a gas which acts as a carbon source, it can also work.
So a rotating furnace where you agitate the powder as you let the reaction happen. Okay. Yeah. As you and Roland discussed, I was well, I guess this question is more to Roland. Then I was really interested in knowing what process parameters would optimize the part of the laser power, the laser beam that is on top of the powder instead of on top of the melt pool. I mean, this is for me something that I still can't quite wrap my head around. How much of the energy is actually coupled into the melt pool, and how much is going into the powder before that. So is it mostly scanning speed, or is there something else?
Yeah, we have played with it in a given range, so we didn't vary too much, but in conditions which are typical for additive manufacturing, actually, if you reduce what the normalized enthalpy, that's what we use to describe the energy density. If you reduce it, actually, you increase the proportion of the energy that goes into the powder.
Okay. Mm-hmm.
Yeah, that actually I showed a graph. Maybe in the discussion part after I can show it again. But then there is a graph that goes. Typically, we are around 40% in the optimal conditions, which are in the near keyhole threshold. But if you go down, then the proportion of energy that goes in the powder is increasing.
And Roland, what did you say? If your normalized enthalpy decreases, then you evolve more towards conduction mode, you say you shine less on the powder?
More.
Okay. I'm just, is that because your melt pool shape changes then?
It is how fast you create the melt pool at any instant as compared to the motion of the laser, right? So it's hard to have an intuition about it.
So it's also it's related to the existence of time that the melt pool exists, right?
Right. It's the time of existence of the melt pool versus the speed of the laser. Exactly. Yeah.
Okay.
But what is interesting is that you always have a significant amount that goes into the powder, and because, as you said, the powder absorptivity is significantly increased because of this multiple scattering. Actually, this contribution is never negligible.
Yeah.
And that's why you can use it to quantify what happens. So even if you measure the absorptivity of your powder at room temperature, you can compare different processing conditions for different materials based on that. You don't need to know the liquid value.
Okay. And yeah, because I've read your paper, do you have some experimental proof of that? Because I'm thinking now about my carbon decorated powder and the carburized powder. The carbon decorated powder in the powder state, it has a very good absorption, but when you look at the processing conditions, you simply cannot process it at moderate scan settings. You need, again, nearly similar scan settings as you need for pure copper. While for the carburized powder, it works with much lower energy densities.
Yeah, I guess that is probably an improvement on the liquid side. I mean, that the absorptivity, I assume. On the powder side, it's probably good, but on the liquid side, it's probably better. And overall, then you increase your absorptivity. When
in the liquid, I can imagine it's horrible because it doesn't wet at all. So they separate immediately. Also find them really at melt pool borders in your solidified microstructure, the carbon particles, I mean. Yeah, okay, yeah, interesting.
Thank you. Any more questions for Kim? Anyway, I think now we're moving without transition to the discussion section.